Black holes, predicted by Einstein's theory of general relativity, are objects that have captivated scientists and the public alike. From their formation to their effects on the universe, black holes are a fascinating area of study. In this video, we'll explore 10 key facts about black holes, explaining the science behind these cosmic giants. Black holes are detected by observing their surrounding environments, not directly. Since light cannot escape a black hole's event horizon, we can't see them directly. Instead, we infer their presence through several indirect methods. One key method is observing the behavior of matter in their vicinity. As matter spirals towards a black hole, it forms an accretion disk, a swirling disk of gas and dust that heats to millions of degrees due to friction. This superheated material emits intense X-rays and other radiation, which can be detected by telescopes. Another way is through gravitational lensing. The immense gravity of a black hole warps the fabric of space-time, causing light from objects behind it to bend and distort, creating observable effects. Finally, the motions of stars orbiting seemingly empty space can reveal the presence of an unseen, massive object, a black hole. Falling into a black hole would result in spaghettification, where you would be stretched vertically and compressed horizontally due to the immense gravity. This dramatic effect is a consequence of the extreme tidal forces near a black hole. As an object approaches the event horizon, the gravitational pull on the side closer to the black hole becomes significantly stronger than the pull on the far side. This difference in gravitational force stretches the object vertically, like pulling on a piece of spaghetti, while simultaneously compressing it horizontally. This process would be fatal long before reaching the singularity at the center. Stellar mass black holes can form in seconds from collapsing massive stars or through mergers of neutron stars or black holes. When a massive star reaches the end of its life, it can no longer sustain nuclear fusion in its core. The star's core collapses under its own gravity, triggering a supernova explosion. If the remaining core is massive enough, typically several times the mass of the Sun, it collapses further into a black hole. These collapses are incredibly rapid, occurring within seconds. Black holes can also form through the mergers of extremely dense stellar remnants called neutron stars. The collision and merging of two neutron stars, or a neutron star and a black hole, can also create a black hole and generate powerful gravitational waves. The formation of supermassive black holes, however, is a more complex and less understood process, though they can reach enormous sizes relatively quickly, in less than a billion years. If the Sun were replaced by a black hole of the same mass, Earth's orbit would not change, but the lack of sunlight would be disastrous for life. According to the laws of gravity, the gravitational force exerted by an object depends on its mass. If the Sun were magically replaced by a black hole with the exact same mass, the gravitational pull on Earth would remain the same. Therefore, Earth would continue to orbit along the same path. However, the crucial difference is that a black hole does not emit light or heat like the Sun. The sudden absence of sunlight would plunge Earth into darkness and freezing temperatures, making it uninhabitable for most life as we know it. Black holes can get smaller through a process called Hawking radiation, where they slowly lose energy and mass. This theoretical process, proposed by Stephen Hawking, suggests that black holes are not entirely black. Due to quantum effects near the event horizon, pairs of virtual particles can pop into existence. Sometimes, one particle falls into the black hole while the other escapes, carrying away a tiny amount of energy. This energy loss causes the black hole to slowly evaporate over extremely long timescales. However, for black holes of stellar mass or larger, the evaporation process is incredibly slow, taking far longer than the current age of the universe. The most distant black hole observed is located in a galaxy called UHC-1, about 13.1 billion light-years from Earth, existing about 690 million years after the Big Bang. This incredibly distant object is a quasar, an extremely luminous active galactic nucleus powered by a supermassive black hole accreting matter. The intense brightness of the quasar, caused by the superheated material falling into the black hole, allows astronomers to detect it across such vast cosmic distances. This discovery provides valuable insights into the early universe and the formation of the first supermassive black holes. Scientists calculate the mass of supermassive black holes by observing the motions of stars in galactic centers. Since we can't directly observe the black hole itself, scientists rely on the gravitational influence it exerts on surrounding stars. By carefully tracking the orbits and speeds of stars near the center of a galaxy, astronomers can infer the presence of an unseen, massive object. Using Kepler's laws of planetary motion and other gravitational principles, they can calculate the mass required to produce the observed stellar motions. This method has been crucial in confirming the existence of supermassive black holes at the centers of most galaxies, including our own Milky Way. Black holes, through stellar explosions and mergers, contribute to the distribution of elements necessary for life and may trigger the formation of new stars and solar systems. The supernova explosions that create stellar mass black holes are responsible for dispersing heavy elements, such as carbon, oxygen, and nitrogen, into the universe. These elements, forged in the cores of stars, are essential building blocks for planets and life. Furthermore, the shock waves from these explosions can compress nearby gas clouds, triggering the formation of new stars and even entire solar systems. Black hole mergers also contribute to the creation and dispersal of heavy elements. The role of supermassive black holes in galaxy formation is still an active area of research, but it's believed they may play a key role in regulating star formation within their host galaxies. Black holes do not pose a threat to swallowing the entire universe. While black holes have immense gravity, their influence is localized. The gravitational pull of a black hole diminishes rapidly with distance. Even supermassive black holes at the centers of galaxies only exert significant gravitational influence on objects relatively close to them. The vast distances between galaxies and the ongoing expansion of the universe make the possibility of black holes consuming everything extremely unlikely. Black holes cannot eat entire galaxies. While black holes have immense gravitational pull, their influence is limited to their immediate surroundings. The gravitational reach of even supermassive black holes at the centers of galaxies is not sufficient to consume the entire galaxy. Stars and other objects far from the galactic center are largely unaffected by the black hole's gravity. While black holes can accrete matter and grow over time, they do not pose a threat to swallowing entire galaxies. So, there you have it, 10 fascinating glimpses into the world of black holes. These enigmatic objects continue to challenge our understanding of the universe, reminding us just how much we still have to learn. What do you find most mind-blowing about black holes? Let us know in the comments below.